Good morning, everyone. My name is Ashutosh Garg. I work as a solution provider with Furnace Improvements. In March this year, our company completed 25 years in fire heater business in the US. We are conducting free fire heater training webinars this year as a part of our Silver Jubilee celebration. Welcome to today's training session on Steam Methane Reforming Furnaces. We have a full house. We have received more than 120 registrations. And I thank you all for your time and interest. Today's webinar is going to be for 90 minutes. So please, and it's an interactive webinar. So please keep on sending your questions all the time. And we will try to answer them, maybe not in this session, but maybe in the next session. So let me start our webinar. So, okay. So we are going to be talking about Steam Methane Reformer Furnace. It's a very unique heater. It's a only heater or one of the very few heaters which has catalyst filled inside the tubes. And those catalyst tubes are surrounded by flames all around. It's a very special heater. We are going to be focusing on this heater today. So let's go and get you started. Let's have a couple of questions to understand. And we want to talk about what is the most common element in our universe. So the choices are silicon, oxygen, carbon, and hydrogen. So we want to see what is the most common element, and most of you have answered correctly. Hydrogen is the most common element in the universe and even in our solar system. Approximately 70% of the matter in this universe is hydrogen, and it is followed by helium, 27%. So 97% of the material is hydrogen and helium. So let's see what is the situation on our Earth. What is the most common element on our Earth? Our options are carbon, oxygen, hydrogen, and silicon. So majority of you got it right. The correct answer is oxygen. We have oxygen in abundance at about 46%, and it is followed by silicon, which is 27%. So combined, about 73% is the two elements on this earth, and oxygen is needed because we want to breathe oxygen, and that's why we have life on our planet. So let's move on. What is the hydrogen content by weight on this earth? How much hydrogen is present? I mean, everybody is talking about hydrogen, so I want to see how much hydrogen is really present in our Earth. Is it 10%, 1%, 3%, or 0.15%? Most of you got it correct. We have only 0.15% of hydrogen by weight. And as you see all the time, we are talking about hydrogen economy. We are talking about using hydrogen to power our entire world, actually. So hydrogen has all become suddenly like a blue-eyed element or blue-eyed gas. Everybody is talking about hydrogen, but hydrogen is very rare, actually. If you think about it, hydrogen is very rare. So let's talk about the next thing. Now we are talking of steam methane reforming, right? So let's see how much hydrogen is present in methane by weight, right? We want to extract hydrogen from methane. So let's talk about how much hydrogen is there. Is it 70%? Is it 50, 25? What is the, and I believe most of you will get it right, actually. Well, almost all of you got it correct. It's 25%. So 25% of methane is actually hydrogen, and 75% is carbon. And it is this carbon which we are concerned about. We are concerned about carbon dioxide, the greenhouse gas emission, because whenever we are going to be manufacturing hydrogen, we will have this unnecessary baggage which we don't want in form of carbon dioxide, carbon monoxide, whatever methane, all these greenhouse gas emissions are going to be. So we have a very tough task ahead of us, that how to produce hydrogen using steam reforming, and at the same time take care of carbon. Where does all this carbon dioxide is going to go, actually? And that's going to be pretty much like 75% of the methane is carbon content, and when it combines with oxygen, it goes even higher. And the other element which we are talking about is water, right? We used steam methane reforming, so steam is water. Let's talk about how much hydrogen is there in water. You have to remember one thing: hydrogen is very light. It has a molecular weight of 2. Well, majority of you still got it right. It's only 11%. 89% of water is oxygen. So to all my colleagues who are talking of producing hydrogen by electrolysis, we will be only making 11% by weight of hydrogen using electrolysis, and electrolysis requires lot of energy, lot of electrical energy. So it is not going to be common currently. Maybe in future it may become economical. So now that I have your attention and we are into the webinar, let me introduce myself. I am a chemical engineer. I passed out in 1974 from IIT Kanpur in India. I started my career in an ammonia plant, which had a steam methane reformer, top source steam methane reformer, side-fired furnace. Then in 1976, I moved to KTI, and KTI has been manufacturing steam reformers, is the leading supplier of steam reformers. I worked in KTI, I worked in Engineers India, then KTI Corporation in US. Since 1996, I've been working with furnace improvements. One of the jobs which I did several years ago was being a consultant to Raytheon and working with them on the largest steam methane reformer in the world. I think it had almost like 1,800 tubes. Really, really big reformer. I've also worked on a hydrogen handbook for a major hydrogen plant operator. That was all several years ago. But what we want to talk about is that we have a contrarian approach. We have a challenging approach. We have always questioned why we are doing some things which we are doing. Why are we designing it like that? We always challenge and try to find out if there is a better way. That's what our whole approach is about. So that's what we want to talk about. So let me tell you a little bit about furnace improvements. Furnace improvements pays my salary, pays our bills. So we have to give it a couple of minutes before we resume. Furnace improvement started in 1996 with a mission to improve performance of existing fired heaters. Since then, we have been focused on revamping fired heaters, increasing their capacity, run length, efficiency. We have been reducing NOx emissions on several heaters. We have 3 patents on improving performance of fired heaters. We have 3 offices. We have a team of about 35 engineers and designers. We take projects on turnkey basis. We also have a CFD office, which we opened it in 2014. It's in Pune. We are one of the few heater companies with its own CFD modeling office. We also want to take this opportunity to thank all our customers for their business and support, and we take pride in doing very high quality technical work, keeping schedule, do it once, do it right. So I also want to take this opportunity to thank our team in New Delhi for working on this presentation. This Kahoot is all because of the hard work put in by our team. I'm just the front end, or I'm just the one who is presenting it today, but they are the ones who developed all the content for us. Thank you, team. You did an excellent job. So our initial plan was to have 4 sessions, and we will still have 4 sessions. And what we did was we broke it into 4 parts. Like in the first session, we will talk about introduction, reaction kinetics, reformer catalyst. In the second one, we were going to talk about radiant section, catalyst tubes, convection section. Third one, we are planning to cover burners, refractory, stack, etc. The last session, we will cover NOx emissions, reforming heater operations, and troubleshooting. So this was basically what our plan, but let's see what we have for you. So I want to ask all of you, what are the operational issues in your steam methane reformers? Like, are you facing issues of methane slippage, hotspots, flame impingement, high tube metal temperatures? So well, we got quite a few responses. Some have high methane slippage, some have hotspots. Hotspots and high tube metal temperatures are basically the same thing, I should say. Flame impingement. And if you see, most of these issues are related to combustion. And we will cover all that in the next thing. Here is something more we want to talk about. What are the maintenance issues in your furnaces? What we have received. Maybe you are replacing your tubes every 2-3 years or 5 years, or you are having refractory failures, pigtail damage. So most of the people are concerned about tube life. I think what I feel is tubes have become like a consumable. Like every 3 years, people just dutifully replace the tubes, without going into root cause analysis. That's typically what happens. Okay, you can also talk about the design issues. If you have any design, like you are having short tube life, you are having methane slip, you are limited on capacity, and or if you are having problems with the burners. So it's basically the majority of the people are worried about short tube life, capacity limitations, methane slip, and burners are again this thing. Some of the major design issues with the steam methane reforming furnaces. So we had asked during the registration process to submit us the operational issues with your steam reforming furnaces. What do you want us to cover in this webinar? And we got such an overwhelming response from all of you. So thanks to all the participants who sent us number of topics. I mean, I don't want to repeat all these things, but we have a whole slate of issues which we will be using it for covering in our future webinars. So we got almost like 300 responses from all of you. We had asked 3 questions to each of you. So basically we got 3, So similarly, these are other operational issues with SMR furnaces, NOx emissions, hotspots. So tons of issues which you have presented to us, and we will be looking at them, evaluating them, and covering them. So basically, we want to cover what you want to hear. That's what our aim is, that to be relevant. Otherwise, we won't be relevant, So we have all these topics which have been submitted by you. So we will be including all the answers to all these questions. Another thing what we have started doing is posting answer to these questions on our Facebook page and on LinkedIn page. So please join the list, and you will see our team has posted a lot of answers from our previous webinars. So it's going to be a really, really good source of information. That's what we want to on the social media pages. So I want to ask you, where is your SMR located? Do you have a hydrogen plant? Do you have a ammonia plant? Yeah, we have SMR and methanol plant, or you may not even have an SMR. Actually, you may be belonging to a design and engineering company or a consulting company. So we just wanted to get a poll actually where our participants are covering. So, well, 50% don't have an SMR, but we have 1% from ammonia plant, 1 from methanol, and 4 from hydrogen plant. So hydrogen plant is a major use of steam methane reformers. So generally, the steam methane reformers are classified or quantified by the number of tubes. Because if I know the number of tubes, I will know approximate processing capacity of your reformer. So the small reformers are up to 150 tubes, 150 to 300 tubes are medium size. They are all on the small size. The larger ones are around 600 tubes. So it's basically the catalyst volume which is controlling the capacity. And if you want to note down, typically each tube has a processing capacity of 4,500 SCFH of syngas. That's typically the capacity of one catalyst tube. So if you know you have got 600 tubes, you just multiply, and that way will give you a capacity of your reforming furnace. Well, thank you for your responses. Now let's talk about steam methane reformers. It's a heart of 4 petrochemical plants. We're talking of ammonia, we're talking of methanol, hydrogen, and even in sponge iron metallurgical plants, we have SMRs located. Ammonia plants produce syngas for ammonia production from SMR. Methanol also produce syngas, a different syngas for methanol production. Hydrogen plants produce hydrogen from this SMR. So approximately methanol is, we are producing almost 12 million tons of methanol using syngas every year. And ammonia quantity is almost like 180 to 200 million tons per annum. So it's a lot and lot of ammonia. So where is the ammonia used? So ammonia has a lots and lots of uses. The major one is fertilizers. Urea is the most common fertilizer what we use. Then we have ammonium sulfates, ammonium phosphates. We have use of ammonia for synthetic fibers like caprolactam, nylon 6, raw material for nylon. So lots and lots of use of ammonia are there. Ammonia is also used for making ammonium nitrate, which is an explosive. So ammonia is a very, very important raw material. In fact, 50% of the steam methane reformers plants are basically ammonia plants. So ammonia have ammonium nitrate, ammonium phosphate, nitric acid, hydrazine, acrylonitrile. So lots and lots of uses of ammonia. Ammonia is also responsible for green revolution, in the world actually. Chemical formula of ammonia is NH3. You can see the structure. We have got one nitrogen atom and it's combined with 3 hydrogen, 3 single bonds. And the molecular weight is 17. It's a colorless gas with a pungent smell. And ammonia is manufactured using nitrogen and hydrogen using Haber's process. Nitrogen is produced by 2 routes. The one which I'm showing over here is secondary reforming. And the second route is separating it from air liquefaction. I mean, you liquefy air and then you use a liquid nitrogen as a source of nitrogen. And hydrogen is still mostly produced by steam reforming. So once we have the nitrogen and hydrogen, now we can mix it and produce ammonia. So production of ammonia is highly energy intensive. The number I have is 6.6 gigajoule per ton. So lots of energy is needed for producing ammonia. The reaction is nitrogen plus 3 hydrogen gives 2 molecules of ammonia. It's a Haber process, ammonia synthesis loop. It's a very high pressure process. I mean, the plant in which I used to work 40 years ago, the ammonia synthesis was carried out at 300 atmospheres, almost like 4,000 psi. There were plants even which had even 600 atmospheres. Although in the last 30, 40 years, there have been a tremendous improvement in catalysts. And as a result of these catalysts, now we are able to generate ammonia at much lower pressure, so almost like 100 or 150 atmospheres. It's still high, but it is much better. The catalyst which is used is iron catalyst. It's an exothermic reaction, so we do have some heat generation. Waste heat production is there. So let's talk about the second, and here I want you to type your answer. This is a little different type of thing. Please type your answer. What are the uses of methanol in the industry? Methanol is also a very important material. I mean, in India, the methanol was used as a spirit, and whenever you would have a cut, you would apply methanol, So, so we got several responses. The ones which I had was terephthalate, DMT, methylamines, MTBE, formaldehyde. Formaldehyde is the major use. 50% of methanol is used in formaldehyde, and formaldehyde is the one which basically makes laminates. If you heard of Decolam and all those different laminates, that's where basically the formaldehyde is used for making these laminates. So there is a little difference, minor difference in these steam reformers. In methanol, we need not only hydrogen, we also need CO. And we need CO in the ratio of, we produced a ratio of 1:2, but what is produced from steam reformers is typically 1:3. So we add some CO2 to consume the additional hydrogen. And methanol market is almost $27 billion a year. So it's a pretty big market, actually. The uses we just talked about, formaldehyde, MTBE and TAME are the anti-knocking agents in the gasoline. DMT is again a plastic raw material, and methylamines. So these are some of the chemical formula for methane is CH3OH, molecular weight 32. It's also known as methyl alcohol, colorless volatile liquid with pungent odor, chemical building block, produced from carbon monoxide and hydrogen, again in the presence of catalyst. So these are the two reactions we have for producing methanol. CO plus 2H2 makes CH3OH, and we can also use CO2 plus 3H2 making methanol, and water vapor. We use copper or zinc oxide, aluminum oxide as this thing. The reactions are exothermic. So methanol has several uses in the industry. Let's talk about the hydrogen. What are the major uses of hydrogen in the industry? One major use we already talked about, and that is ammonia. We have already talked about ammonia, but the second major use is in the refining industry, where we use for hydrotreating. And hydrogen is being talked about as a clean fuel of future. So we are going to be seeing a lot of hydrogen production in the future. That's why we are doing this webinar. So hopefully we think there will be a lot more steam reforming furnaces in the future for producing hydrogen. Hydrogen is a clean fuel. There is no carbon, there is no nitrogen, there is no sulfur components, so that produce environmental risk. It's a clean fuel. I heard that Japan is betting big on hydrogen, and they think they may be able to convert your existing automobiles from gasoline to hydrogen by putting some kit, so they are betting big on hydrogen. So currently, hydrogen is used in the refining industry. And there are several processes in refining, like hydrotreating. We are talking about hydrodesulphurization, hydrocracking, deep atmospheric residue conversion, and all these are requiring a use of hydrogen to produce useful products. One of the two things have changed in the refining in the past 30 years. One is we have tons of cokers. So we are trying to minimize the coke formation from the crude. And second is we have started processing heavy crudes, very heavy tar sands. So what that happens is, in order to make marketable products, useful products, you need a lot of hydrogen. You need hydrotreating because you want to remove sulfur. So even for removing sulfur, you have to put hydrogen so that the sulfur combines with hydrogen to give you H2S. So that's typically how hydrogen has been used extensively in the last, I would say, 30, 40 years. And most of it is because of heavy crude, what we have started processing. So that's basically is leading to hydrogen. Hydrogen is very light. Molecular weight is only 2. Colorless, odorless, tasteless, non-toxic gas. I think it's a very fun fuel. Releases great amount of heat, hot flames, future fuel. The only product of combustion is hydrogen, the water vapors, and steam reforming is one of the major ways in which we are generating hydrogen. So very important. And here can show you how the hydrogen demand has gone up in last 40 years. We are almost like 4 times. Every 10 years, the demand is doubling, actually, you can see. And there are 2 major users. We have ammonia and we have refining. If you see the chart, you will see basically the 2 major users. Others are very minor. So let us talk about the furnaces now, or the SMR Steam Methane Reformer. We have been talking about end products, and the purpose of steam reforming is to convert hydrocarbon feed into hydrogen-rich synthesis gas. It's carried out in a direct fired catalytic reactor in the presence of steam. So we need to understand what process is taking place, So we will talk about the chemistry of steam methane reforming, talk about catalyst, talk about steam to carbon ratio, operating conditions, and design parameters. So this, in most of the furnaces, we are heating. We are just doing sensible heating, or we are doing vaporization, but this is a reaction furnace. What goes in doesn't come out. So we are feeding steam and we are feeding methane, but what comes out is hydrogen, carbon monoxide, carbon dioxide, and unreacted methane. This reaction is endothermic. It takes place at high temperatures, and the heat is provided by burners firing downward, sidewall, or upward, depending on the design. So this is basically the steam methane reforming furnace. So typical flow is we take the hydrocarbon feed, preheat it in the convection section, then we do the purification. Now, we'll talk about it, but we need to purify and remove all the sulfur, almost down to 0.2 parts per billion. That's how much sulfur because sulfur is a poison for the nickel catalyst. So we want to remove this thing, then we mix steam, again preheat it up, and then send it into this tubular reactors. This is a tubular reactor where we are providing heat for the endothermic reaction. And then we generate steam at the outlet to recover the heat. But that's basically the typical flow scheme. And the flue gases are cooled down and then vented to the stack. It appears that in future, we may not be able to even vent it to the stack. We may be recovering CO2 from these flue gases and then sending only the rest of the stuff, oxygen, nitrogen, and water vapors into the stack. And the CO2 will be sent to the pipeline. So that is the future of flue gases as I see in the next 15, 20 years. So one of the parameters we want to talk about is what is steam to carbon ratio? What does it define? Is it weight of steam to weight of carbon, weight of steam to weight of hydrocarbon, moles of steam to moles of hydrocarbon, or moles of steam to moles of carbon? So so most of you got it right, actually. I would say steam to carbon ratio is defined as moles of steam to moles of carbon in the feed. That's basically what steam to carbon ratio means, actually. And let's go over and ask you a couple of more questions on. So we have a reaction given over here, which is methane plus water produce carbon monoxide and 3 molecules of hydrogen. It's an endothermic reaction requiring almost 97,000 BTUs per pound. So I'm asking you, what is the steam to carbon mole ratio in the below reaction we just talked about? So almost everybody got it correct. It is 1. So if you look at the equation, we have 1 mole of methane, and that 1 mole of methane has only 1 mole of carbon, and then 1 mole of water, which is 1 mole of steam. So the ratio is 1:1. So if you think about this reaction, the basic reaction which is taking place, theoretically, steam to carbon ratio, what is needed is only 1. But what happens is there is another reaction which is taking place, which is called water gas shift reaction. And if we combine that reaction, we get 1 methane plus 2 water molecules going to carbon dioxide plus hydrogen. So we are generating more hydrogen because of water gas shift reaction. So now here, So, well, everybody got it right except one. So it's basically two. Now we have got two molecules of hydrogen combining with 1 mole of methane or 1 mole of carbon. So the steam to carbon mole ratio is 2. And we'll talk about a little bit more that theoretically we only need 2. So why are we talking about 3, 4, 5? So we'll talk about and try to answer those questions in a little while. But let's move on. Uh, so we have the feedstock. The feedstock, as we talked about, is methane. So there are two commonly used feedstocks for synthesis gas. It used to be naphtha. Naphtha, steam naphtha, and it's still naphtha in most of the lot of places. But now, in the past 5 to 10 years, natural gas has overtaken naphtha as it is widely available and cheaper because of shale gas. We got so much shale gas that there is a big boom in natural gas. There is a big boom in ethylene. There is a plenty and plenty. I mean, tons of this thing. So globally, right now, 67% of the hydrogen is produced from natural gas. And natural gas is basically methane with some heavier hydrocarbons like ethane and little bit of CO2, And as we talked about, even methane has only 25% hydrogen. Methane actually has more hydrogen content by weight than naphtha actually. So in a way, it is even better than naphtha. Naphtha has much less, hydrogen than as compared to methane. So we already talked about the first reaction, which was reforming of natural gas. And there we are producing hydrogen. Then another reaction which is taking place is this CO, which is being generated, is reacting with more water vapors to generate more CO2 and more hydrogen. So if we add the two reactions, now this is exothermic reaction. If we add the two reactions, we get methane plus 2 water vapor going to CO2 plus 4H2. So we get more hydrogen, And our aim is to get as much hydrogen as possible. So we get these two reactions and we are generating 4 molecules of hydrogen using water vapor. So that is the net reaction which is taking place. So this is a water gas reaction, what we call it, shift reaction. And they both combine to give you more hydrogen. So typically out of steam reformer, what comes out of steam reforming is the gas, which is a mixture of hydrogen. If you see, predominantly we get about 47% hydrogen. Then we get carbon monoxide, we get carbon dioxide, we got methane, we got water and some nitrogen. So that's basically the output of steam reformers. And if you compare this with different uses, you will see some very good similarity, Now, steam reformer does produce a lot of CO2 for as a side product, So these are the three major industries where hydrogen steam methane reformers are used. And you will see over here, methanol has a different operating conditions. Hydrogen has little bit different, and ammonia has different. The major difference you will see in hydrogen and ammonia is the methane content. Typically, in ammonia, we leave the methane at 8 to 12% because we want to combust this methane to generate carbon dioxide and also get nitrogen. So we do a secondary reforming process, and we also generate more hydrogen. So during the secondary reforming, we need this methane. So as a result, the outlet temperature of ammonia reformer is lower as compared to hydrogen and methanol. Hydrogen and methanol reformers are operated at higher this thing. Things may change because they are trying to be bringing different technologies like PSA and air liquefaction. So then the source of nitrogen may change. But this is basically, if you see the difference in minor difference, over here. We get less CO in ammonia and then more CO in methanol, methanol and hydrogen. So it's a gas phase reaction over a solid catalyst. And we need high energy rates for reaction. The typical heat of absorption per mole of CO and hydrogen is almost like 32,000 BTUs per hour. And out of this, sensible heat to get up to the feed temperature of 1550 is almost like 25%. So that's 25% of the heat what we are supplying is getting into just a sensible heat. And you can see that these are the two molecules, methane and water, and then we get hydrogen and CO2. That's what we are getting. So I just want to give you utility requirements. If you see for a 50 million standard cubic foot per day hydrogen plant, the feedstock needed is 730 million BTU per hour in terms of energy. Almost 20% is the fuel which is needed. And then it exports steam. So a lot of steam gets generated. And the reason for that is the feed is at ambient temperatures. If you look at the natural gas or methane, it is at ambient temperature. And if you see the products leave the reformer at about 14, 15, 1600 degrees F, but then they have to be cooled so that they can be processed further. We cannot use that 1600 gas anywhere in the CO, methanol, or hydrogen. We need them at the lower temperature. So it has to give out that high temperature products have to give out heat, and that leads to a lot of steam production. So it is not a matter of choice, but as a matter of necessity, because we are going to take the feed and heat it up all the way to 1500 so that the reaction can take place. And then again, we have to cool it down. And also we have to cool down the flue gases so we generate more steam. One from the product, one from the flue gases. So almost 120,000 pounds per hour or 54 tons of steam is generated in a 50 million standard cubic foot per day hydrogen plant. I don't have the number in metric, but maybe next time we can put this number in metric also, 50 million. So let's talk about how we are designing reformers, or what are the parameters which are responsible for converting the methane into hydrogen. And we talk about three parameters here. We talk about temperature, we talk about pressure, and we talk about steam to carbon ratio. So three parameters we want to talk about. And this is a chart which we have put. Basically, we have pressure, we have temperature, and we have steam to carbon ratio. So these three parameters, if you use, you can go whatever is the temperature, let's say 850 degree and 35 bars, you go up to 3.5 or ratio, and you can see the equilibrium methane will be around 5%. So you can use this chart to get the methane at the equilibrium, what will be the methane. So basically that's the chart which can help you just look at what will be the theoretical methane which will be in the product on the dry basis. So, but what we talk about theoretical product, theoretical concentration, and we're talking of actual concentration, and between the two, we call it approach to equilibrium. And that means, let's say we get 1500 degrees for getting 5% methane we just saw in the chart. But in reality, you will see that temperature has to be 10 to 15 degrees higher at the start of run. At the end of run, it could be even 35 to 50 degree higher. So that difference in temperature is basically the approach to equilibrium. And that happens because the catalyst keeps on getting deactivated over the time. So the catalyst keeps on getting deactivated. So most of the reformers we will be designing for about 35 to 50 degree higher actually. If we get 1400 degrees outlet temperature for getting the methane, we will design it for 1450 so that you as a client never falls short on the methane. You can, in the beginning, you can run at a lower temperature, and then as the catalyst ages, you go higher. So you can see this is the equilibrium temperature, and this is the gas temperature. So basically, we try to lower approach will get you lower exit methane in the product. So in the new plants, your temperature will be lower, and as the catalyst ages, your temperature will keep on going up. So methane slip, at the start of run, we will be very close to equilibrium conditions, but as the condition at the catalyst starts aging, the methane concentration will go up, or we will have to raise the temperature. Typical operating conditions, steam to carbon ratio of 3:5, outlet pressure of 290 to 550, and outlet temperature of 1500 to 1650 degrees. That's typically the operating conditions, what we have for steam reforming. So if we go for a higher outlet temperature, what will happen to the methane content? Will it go up? Will it go down? Will it not have any effect? So only 2 of 10 people got it right. As the temperature goes up, the methane content will keep on going down. Remember, this is an endothermic reaction. Endothermic reaction means it needs heat. So the more you heat, more reaction will take place. So the methane content will go down. Higher temperature. Okay, so higher temperature will always help our methane this thing, but we have a limit. We have a limit on the temperature, and we'll come to that. But let's talk about more things. We talk about If we increase the outlet temperature from 1400 to by 50 degrees to 1450, methane content will drop from 10% to 7.5%. So we have more conversion taking place. Similarly, if we increase the steam to carbon ratio from 3 to 4, methane will drop from 10 to 7%, 7.5%. If we do both, then it will go even higher. Other thing, if you see, if we decrease the outlet pressure from 400 psig to 300 psig, methane content will drop from 10% to 8%. So you can see the parameters which are affecting the methane conversion. And it is simple chemistry. The simple chemistry is if it's an endothermic reaction, higher temperature helps. If you looked at the equation, 1 CH4 plus 2 H2O give us 3 molecules of hydrogen plus CO. So 2 molecules, 3 molecules goes to 4 molecules. That means the volume is increasing. So anytime in any reaction, if the volume goes up, the lower pressure will help. So if you decrease the pressure at the outlet, it will help. However, it is not commercially viable to work on a lower pressure, and that's why we still continue using higher pressure. Feed purification, we have to have the feed to be really, really purified. We are going to go down to 0.2 ppm on sulfur, 0.2 ppm on chlorine, heavy metals less than 0.1. So we have a zinc oxide bed, and we try to take that sulfur out from our natural gas or from naphtha. And these are the reactions which are taking place. This hydrogen reacts with the mercaptan compounds, converts it into H2S, and that H2S is absorbed in the zinc oxide bed. So it's a very, very established technology which is used for removing sulfur. So sulfur has to be removed. If the sulfur goes to the catalyst, your catalyst will get deactivated. So we have to make sure that the poisons, which sulfur is one of them, does not go to the. There are some other reactions taking place. Let's just go over quickly. One is the hydrogenation of olefins. The important one is carbon forming reactions or CO reduction reactions, because another thing is carbon. Another problem with the catalyst is carbon. If you have carbon deposit on catalyst, your catalyst is gone. The catalyst is a surface phenomena. If your surface is clean, that's where the catalyst is active. If you cover the catalyst with soot, carbon, anything, catalyst becomes deactivated. So it's a very, very simple this thing. So what happens is if you have got any olefins in the feed, they will combine with hydrogen to make ethane. So you don't want this thing to be happen. So you want to make sure that olefins are removed from the feed gas even before you process it. You don't want to be consuming hydrogen. Similarly, carbon forming reactions are very, very important. There are two reactions we are talking of: methane cracking into carbon and hydrogen. We don't want this to be happening at all. Or the second reaction is Boudouard reaction or CO disproportionation. Basically, it happens at high temperatures, and here you can see CO is converting into carbon and carbon dioxide, and that carbon monoxide also meets with hydrogen to convert carbon and H2O. So you don't want these two reactions to be taking place. They could be, if you have carbon formation, you will get problems. So we have to make sure that these two reactions don't take place at all. So let's talk about the function of the catalyst. Why do we even use catalyst? So we could have combined methane and steam, but to combine it, we will need very, very high temperatures, or we will need very, very different conditions. So the catalyst, what it does is catalyst alters the reaction rate. Catalysts do not take part in the reaction. They don't get consumed. They basically lowers the activation energy of the reactant. So if you see over here in this chart, we have reactants over here, and without catalyst, it will be much higher. But with catalyst, we lower the reaction activation energy, and that is why we get conversion. Okay, so without catalyst, we will have to go to extreme conditions, and the conversion may be very, very low. So what are the requirements of a catalyst actually? So there are several requirements we can talk about. High activity, that is the most important one. Good heat transfer. I mean, you want to make sure that it is also getting heated and cooled at the same time. Low pressure drop. You don't want too much pressure drop. Low carbon formation and high physical strength. These are all very important things. One of the things which happens in the carbon is, in the catalyst is, anytime you have a shutdown of your steam reformer, the expansion and contraction of the catalyst takes place. So every time you do that, you will have some breakage of the catalyst. And generally, the reformer pressure drop will continue to increase every time, maybe by about 5%. So those are some of the things. And the conditions are so extreme, you want high physical strength, you want high activity, all these type of things is what you need. So let's talk about what catalyst is used in reforming process, steam methane reforming process. Well, almost all of you got it right. It's a nickel catalyst. Yes, even though we can use platinum, rhodium, some of these catalysts, but nickel is the most common catalyst which is used in the steam methane reforming. So nickel-based catalyst, and the base is typically alumina or zirconium dioxide or magnesium dioxide. They are used as catalyst supports. So that's the shape of catalyst you can see over here. This is very different from what I used to see 40 years ago, more than 40 years ago. Though that time the catalyst used to be Raschig rings, but now you can see they have much different design to maximize the surface. They have got holes, so basically the number of active sites is much more, that catalyst is much higher active. So reformer pressure drop again is an important parameter, depends on the number of tubes, tube diameter, and catalyst types. Those are the three parameters. So let's find out from all of you what is the pressure drop across that catalyst tube in your SMR furnace. So the typical pressure drop in the industry, what we use is anywhere between 30 to 40 psi. I see everywhere, but 30 to 40 psi or 2 kgs, 2 to 2.5 kgs per centimeter square is typically the pressure drop used in most of the reformer designs. You don't want too high a pressure drop, and you also don't want a very low pressure drop. One of the important things about catalyst is to making sure that catalyst does not lose its activity. And there are several reasons which can happen. Some of them is sintering. Sintering is high temperature exposure. A lot of times because of high temperature, the catalyst gets sintered. Others are sulfur we talked about, carbon or coke depositions, and thermal aging. And all these things leads to decrease in the activity of the catalyst, and you are forced to change the catalyst. So let's find out how often do you change your catalyst in your SMR furnace. All right, so most of the people are changing 2 to 4 years. There are some who has never changed it, but I think 3 to 4 years or maximum 5 years is the life of the catalyst. That's what I've seen in the experience. Although some people have changed it even after 2 years also, or less than 2 years. That could be because of mal-operation or power failure or some maybe water going into the catalyst, those type of things. So the SMR furnace design factors, there are 4 major important factors. We're talking about steam to carbon ratio, operating pressure, outlet temperature, and radiant heat flux. These are the 4 important parameters that you want to design. So inlet outlet temperatures, the inlet temperature is typically around 1000 to 1050 degrees F. We want to maximize the preheating in the convection section, and so that the catalyst size or the reformer size is minimized. Outlet temperature is typically kept around 1550 to 1575. And historically, these temperatures are decided based on the metallurgical limitations, actually. The good news is that a lot of development has taken place in the metallurgical industry, and we have lots of exotic alloys. 40 years ago, it used to be HK40, then we get HP modified, but now we have microalloys. So basically, if we can withstand higher temperature, we can go for higher outlet temperature. So it's basically thanks to the metallurgical engineers and developing metallurgical alloys, we are, So one of the important parameter is radiant heat flux. And if you have a lower heat flux, you will get extra catalyst volume, lower tube wall temperature, and lower tube wall thickness. All good things are happening, but the furnace becomes expensive. Nothing comes free. If you got higher heat flux, you reduce the number of tubes, you increase the tube metal temperature, your tube wall thickness also goes up, and the flue gas temperature is higher. So the furnace size becomes smaller, but then you pay price in terms of higher tube metal temperature and higher tube wall thickness. The typical values in the industry are 20 to 26,000 BTUs. Lower number is always better, in my view. Higher number always produces problems. Some people even go up to 30,000, not me actually, but that's typically, yeah. So let's talk about the tube design parameters. We talked about tube length. So typical tube length is around 30 to 40 feet. And it's basically decided by the pressure drop, thermal expansion, and compression load. If you've got a too long tube, then catalyst at the bottom will get crushed. So we have that compression load. So we don't want too long a tube. We don't want very high pressure drop. Also the tube diameter, if you increase the tube diameter, you're increasing hoop stress. You're also lowering the velocity, lowering the heat transfer coefficient. It will give you higher metal temperature and higher catalyst volume. So higher catalyst volume is good actually, don't get me wrong, but basically everything else is not good. So typically the tubes are 3 to 5 inch ID. And the wall thickness is typically in the range of 11 to 18 millimeters or 0.3 to 0.5 or 0.6 inch. So as I said, there has been a tremendous amount of development which has taken place. Uh, Historically, we started with 2520. Then we went to 2424 IN 519. HP modified has been used, and now we are able to use microalloys with titanium and zirconium. So these are rare metals. And what it does is basically we are able to get higher stress values leading to lower tube thickness. And we are using this improvement in metallurgy to revamp reformers. Like if you have a HK40 tube, you go to HP modified or microalloy. Now you can keep the same OD, but you can use the lower thickness. And with that, you can put more catalyst. So you can increase the capacity of your reformer by going with lower thickness and improving. So the catalyst tube has a very important function actually. We basically hold the catalyst and gases under high pressure, efficient heat transfer, you know, and the typical tube metal temperature is generally outlet temperature plus 110 degrees. That's typically the tube metal operating tube metal temperature. Typical design margin is about 30 degrees on this temperature what we take. Steam to carbon ratio, high steam to carbon ratio favors products in reforming. If you see 1 and 3, basically we get much more this thing. Lowers the amount of unreacted methane or methane slip. But the most important thing is occurrence prevention of carbon forming site reactions. That's the most important thing why we use higher steam to carbon ratio. So you can see the effect of steam to carbon ratio. This has been done by an engineer, Samantha Moore, and she has simulated 5 cases. She simulated a lot of cases, but I basically picked up 5 using steam to carbon ratio of 1 to all the way to 5. And basically that shows how much methane slippage is over the time. This is the steam gas or the steam what we are using. This is the heat duty of the reformer furnace. As we keep on increasing, the heat duty keeps on this thing. And then basically slip to duty. So basically how much slip to duty in ratio of pounds per million BTU. And then we plotted, and you can see after 3, there is no significant benefit. And that's why the steam to carbon ratio is generally limited to 3. After 3, basically there is no benefit in terms of operation. I mean, from 1 to 2 to 3, you can see significant benefit in methane slippage. But after that, there is no benefit, on the steam to carbon ratio. So that's why we use 3 or something. So these are some of the benefits on steam. Basically so 3 is a very typical ratio, and control is very, very important in terms of operation to keeping it. All right, we have a quiz time. So let's get back to you. What are the conditions which are favoring hydrogen production? Is it low temperature, low pressure, high temperature, high pressure, or high temperature, low pressure, or low temperature, high pressure? High temperature, low pressure. Thank you all. You got it all correct. Most of you got it correct. So let's move on. Thank you. So reforming reaction is favored by low pressure because the volume of the gases which are being produced increases. So lower pressure is better, but because of the processes which we are using, like ammonia loop or methanol loop, the industry still prefers high pressure reforming because they feel the compression cost of natural gas is much lower as the compression cost of the syngas, which is much higher in volume. So that kind of makes a difference, you know. So you can see as the pressure goes down, the methane conversion goes up. You can see over here. Similarly, temperature actually. So as the temperature goes up, the methane conversion goes down, or methane conversion goes up, so slippage goes down. So higher pressure is good for us. Higher temperature is good for us. And these are the effects of temperature, pressure, and steam to carbon ratio. You can see by going from 1400 to 1600 to 1500, lower temperature, we get less hydrogen. But if you lower the pressure, we get more hydrogen. So that's basically, have you already talked about high temperature, low pressure, and high steam to carbon ratio helps. This is a composition of the products with using different feedstocks. Refinery of gas already has hydrogen, so we get almost 80%. Methane and naphtha, butane. So basically different compositions. And you can see as the catalyst ages, the hydrogen concentration starts going down. Actually, methane concentration starts going up. So this is basically the effect of the catalyst activity. So let's talk about the steam methane reformer furnace. I think we have covered the initial chemistry, the catalyst, and let's talk about the different type of furnaces. And here I have got 4 furnaces for you: floor fired, down fired, terrace wall fired, and side wall fired. So the common thing over here is the catalyst tube configuration does not change in any of the designs. Whether you're looking at the floor fired or down fired, the number of catalyst tubes, the size, all those type of things are the same. What is changing is the firing pattern. In this one, we are using floor fired. This one is down fired. This one is terrace wall fired, or this is side wall fired. So basically, it's the fire side which is changing in all these designs. The catalyst tube, the catalyst configuration, the catalyst length, tube wall, everything remains the same. There is not much difference. So one of the most common design is down-fired reformer. And down-fired reformer is tubes are in a row, several tubes, and the burners are firing down from the roof. And because we can have one row of burners, one row of tubes, one row of burners, one row of tubes. The whole firebox is very, very compact. You can see over here, we need very few burners. And one of the things what they talk about is that the flames are the flue gas and the feed are going in the same direction. So we get maximum heat transfer in the bottom. So we have a very uniform tube metal temperature profile. However, in my experience, most of the problems occur in down-fired reformers, and we will talk in more detail in the future webinars. But you get what you pay for, actually. So if you are saving on the initial cost, you end up paying more. So there are several disadvantages: high heat flux, high TMT. You cannot do you cannot adjust the heat flux in these reformers. Also, the burners are located on the top, and the cold flue gases come out from the bottom. So most of these down-fired reformers are natural draft. One thing I can tell you is, if you have any down-fired, even though you're firing down, but because of the high temperature, flames have a tendency to go up. So no matter what you do, the flames will tend to go up. And when you have that, you will always end up with flame impingement in these reformers, unless they are designed very, very nicely. So most of the reformers, they suffer from flame impingement problems, high tube metal temperature problems, because that's just the nature. I mean, you're trying to have the flame straight, but it is not possible to have the flame straight because you're firing down. So anytime you fire down, you will see they are trying to go up. Side fired reformers have been there for ages now. I mean, in fact, most of the reformers in methanol and ammonia plants were side fired. They were pioneered by Halder Topsoe. They work on natural draft. That's another difference between the down fired and as you can see, there are basically lots and lots of burners on both sides. And generally, we have 6 rows of burners, and these burners are spaced at about 4 to 5 feet. That's generally how these burners designs operate. You can see there are burners in the center. So the difference in these things is there is only 1 row per box. That's a major difference. And because of that, the cost of side-fired reformer is always higher. But you can see this can be natural draft. The convection is located on the top and the stack can be located on the top. So there are advantages and disadvantages of each type of design. Terrace wall is another design which was pioneered by Foster Wheeler, and it basically has terraces. Each terrace is about 10 to 12 feet. So we can have 2 terraces or we can have 3 terraces. Most of the reformers have 2 or 3 terraces, and that's where the burners are installed over here. And there you can see over here, and the burners are firing along the refractory. Another difference I want to tell you, the difference between down fired and side fired is, or the terrace wall is, here it's a refractory which is radiating to the tubes. Whereas in down fired, it is the flue gases which are radiating to the tubes. Although the basic, I mean, if you go theoretically, it's still the same, but the refractory surface is much higher. AR, the refractory surface is much higher. So that's another major difference. And these things can be natural draft. They can have convection section on the top. So there are some advantages of terrace wall reformer, We can have the convection here, and then we have the stack on the top. I mean, the largest reformer I told you in the world, which I worked on several years ago for methanol, had 1800 tubes, was a terrace wall design. So you can make these. Another thing which is dictating the design is the modularization, which heater can be modularized better actually. Bottom fired reformers are not very common. They are mostly used for small capacities. Although the firing is very good actually. I mean, the only disadvantage is the hot flue gases are in touch with the hot tubes. So it's basically counter current, so it becomes kind of limitation. But for small capacities, you can always have a bottom fired reformer, not a problem actually as such. And then the convection section, actually we will talk more about convection section in other this thing. So it is very large and has a lot of services for recovering the maximum amount of heat from the flue gases, generally steam generation. So furnace draft furnaces could be bottom induced draft or natural draft. And there are some furnaces who could be even balanced draft, down fired reformers. You can have air preheat, and then you have the forced draft firing and the induced draft. So we can have both types of furnaces, natural draft or balanced draft. Well, thank you very much for giving me a patient hearing. Now, I want to ask you a little bit how we did. Did this webinar match your goals, or how was it good, or we still need some improvement? Please give us your feedback. Almost everybody said good. Thank you very much. I am going on a 2-week trip, so this feedback will be really, really helpful. So thank you all. Was the course content clear and easy to understand? I mean, my team has worked very, very hard for the last 4 weeks. So we need your feedback and we want to improve it, So again, thank you very much. We will still continue to improve as our name suggests. Furnace improvements, we always keep on improving our stuff, And then finally, a test for myself. So I'm not a very good speaker, actually, although I try. So well, thank you all. Thank you for your wonderful feedback, and hope you learned something new, and we please keep us in mind. Furnace improvements can help you improve the reliability of your furnaces. We can improve the capacity, we can reduce the emissions, we can improve the run length. So we have been there for 25 years now. We are not a new kid on the block. So give us a chance. We can definitely improve the performance of your heaters, reformers, cracking heaters, anything we talk about. We have a wonderful team. We can do CFD modeling. If you have any need for burner flame impingement, high temperatures, anything like that, please give us a chance. Please talk to our people in India or in Pune. Amarveer Chilka is our business manager for India. He can help you. He is a very nice guy. So again, thank you very much. It was really a pleasure doing this webinar, although it takes a lot of effort. So hopefully we will continue. Thanks. and goodbye.